Okay, hi everyone. I am recording today's not quite a lecture, but it is a guide for COMSOL electrostatic simulations. As I mentioned in class last time, you will be doing this simulation in one of the second floor computing labs. So let me give you the room numbers just a minute. There are two computing labs on the second floor. Both should have COMSOL installed. And let me just get you the room numbers here. 2351 and 2359. Both labs should have COMSOL installed. Okay, so what are we doing today? We are going to simulate the electric field and the scalar potentials of a quadrupole. A quadrupole consists of 4 electrodes. 2 of the electrodes have a high voltage, so the top and bottom electrodes have the high voltage, and the 2 side electrodes have a lower voltage. All right. Each one of these electrodes are 10 microns wide by 1 micron tall. The spacing between them is 12 microns, as you can see here. So these types, as you could probably imagine, we could try to solve this analytically by hand. But today I want to show you how we can use a numerical tool like COMSOL to do these solutions for us. Now in industry, often when you design an electronic part or you're designing an electronic PCB, the geometries are too arbitrary and too complex to be solved by hand. So that's why a numerical solver like COMSOL is very useful. So what is COMSOL? It is a PDE solver, so a partial differential equation, as if you recall from some of your earlier studies in your undergrad. Partial differential equations describe all laws of nature, including those in electrostatics. So all of these laws of physics can be expressed as partial differential equations. And if you have a way of solving that, then it's a single tool. COMSOL was designed to be a PDE solver, but it's able to solve these PDEs across all domains, not just electrostatics, but also mechanical stress and strain, fluid mechanics, heat flow, magnetics, chemical diffusion, and much more. I don't have time to go over all these equations. If you're interested, I can talk to you more about that further, but it is very interesting that all the laws of physics can be modeled as partial differential equations. And some of the equations and techniques that we use in the electrostatic domain can be used in the fluidic domain, and can be used in the mechanical domain. All right, so we're not going to go over all the details of that just today. We're going to focus on COMSOL. So what does the COMSOL electrostatics module solve? It solves Ohm's law and it solves Gauss's law, both of which you are familiar with by now. In fact, in this electrostatic simulation, where there's no current involved, we are only going to be solving Gauss's law. Del dot epsilon E is equal to rho. All right, and as you know, in a chargeless system, this can also be expressed as Poisson's law. Del squared V is equal to rho over epsilon, or in the case of a chargeless system, rho over del squared V is equal to 0. The time-dependent solver also includes the continuity equation, but we're not going to be spending too much time on that today. So the steps in the finite element analysis, so COMSOL is a type of finite element analysis solver, is to make a geometry, add the boundary conditions, mesh the model, compute the solution, and then plot the results. And so over the next, this probably won't take very long, maybe 20 to 30 minutes we'll spend in, and I'll show you how to do a finite element analysis within electrostatics using COMSOL. All right, so let's go to COMSOL right now. So when you go, you should be able to find COMSOL in the Start menu. So look for COMSOL Multiphysics 5.2a after you log in. And then when you open it, you'll be asked to, you can create a new model, and that will take you to this page here. All right, so we're going to click on the model wizard, and we are going to be doing a 2D simulation today. All right, and you'll notice that there are several modules available in the COMSOL license that we currently have at Wayne State. Select the AC/DC module, and within here select Electrostatics. That's going to be the interface we're going to be using today. If you read this, it'll say the Electrostatics interface is used to compute the electric field, the electric displacement field, and potential distributions. So in terms of the Maxwell equations, the electric field is E, the electric displacement field is D, and the potential is V. In dielectric materials and under conditions where the electric charge distribution is explicitly prescribed. The formulation is stationary, but for use together with other physics, also eigenfrequency, frequency domain, small signal analysis, and time domain modeling are also supported in all space dimensions. The physics interface solves Gauss's law for the electric field using the scalar potential as the dependent variable. All right, so we're essentially just solving Gauss's law here. We're going to add the electrostatics interface by highlighting this, and click Add. All right, so now we've added the physics interface. COMSOL is actually able to solve coupled problems as well. So we could add multiple interfaces. Let's say if we want to study flow, the coupling between electrostatics and flow. If we wanted to include some electrochemistry in there, we could do that. COMSOL is actually a very powerful software. We're only going to be using just the electrostatics interface, very simple simulation today. And we would like to do a stationary, a DC simulation. All right, it's used when field variables do not change over time. So we are doing electrostatics, so it is appropriate to use a stationary simulation here. So click Done. All right, and now you'll be brought to the main COMSOL window here. Okay, so now if we go back to the steps in making a finite element model and solving it, the first thing we're going to do is make a geometry. So we saw this, this is the geometry that we want to simulate here. We want to have these 4 electrodes, and we also have to have a material here that represents the air in between the electrodes. Okay, so we're going to end up with 1, 2, 3, 4 plus 1 rectangle representing the air. So what we're going to first do is create that geometry. So you'll notice that the model builder, the COMSOL model builder here, has the name of your the model up on the upper left. We haven't named it yet. We could call this quadrupole simulation. I'll just put my author name here. We don't need to set a password here. And then we can also save this file. And so I'll save this under quadrupole simulation B. All right, so we've saved the file. I recommend saving frequently. Global definitions, we won't get into this yet, but if you would like to parameterize your model, if you want to say that the distance between 2 electrodes is some variable d, you can do that. We won't do that in this first one. We'll keep things simple. So we're going to skip over global definitions here, and we go to the component. Component describes the thing that you're going to simulate, the geometry, what materials you're going to be using, the physics that you're going to simulate, and then here is the meshing. We'll get to that in a second. Next is the study. The study is what type of simulation you want to run. We had chosen a stationary simulation, and this part of the tree shows you the results. So we're going to be going through the tree from top to bottom. So within this component, we can label the component what we want. We could call this quadrupole if we wanted to, but it's not important that we label it. It's just something for, it just shows up here. Now, when we get to geometry, we want to create, as I mentioned, 4 rectangles representing each one of the electrodes, and then we also want to create a rectangular square area to represent the air. So what we're going to do is create a bunch of rectangles here. So I'm going to go to geometry one, right click, If you right-click, you'll get this menu where you can select what type of object that you would like to draw. So we would like to create a rectangle here. All right, and we don't need to really label our rectangles. It gives arbitrary names if you don't name them yourself. And the width of this rectangle is going to be 100 e to the negative 6. That means 100 times 10 to the negative 6 meters. So 100 microns wide. I'm sorry, 10 microns. Let's make that 10 microns wide and 1 micron tall. All right, that's the width and the height of the rectangle. And we're going to put the corner at negative 5 microns. So we're positioning the rectangle here. And we're going to put this at 6 microns. Click Build All Objects, and you'll see that this rectangle is made. So notice the positioning is exactly where we put it. X equals negative 5 microns, Y equals 6 microns. So the rectangle is positioned here. The width of the rectangle is 10 microns, and the height is 1 micron. So we are going to go ahead and make all the other rectangles too. I've already, I've pre-decided what the coordinates are going to be, so we can do this fairly quickly. The next rectangle is also going to have a width of 10 microns, and it's going to have a height of 1 micron. This is going to be the bottom, we're going to draw the bottom rectangle here. And the position of this is going to be the lower left corner of that rectangle is going to be at negative 5 microns and negative 7 microns. All right, now we've built 2 rectangles, but we can only see one. One of the hint I'm going to give you is this button here. It says it's called Zoom Extents. This would be to zoom in. This would be to zoom out. This is to zoom just in a selected area. And this one is Zoom Extents. So this will zoom out so that you can see all the objects that you've created. So click on that, and you'll see your 2 rectangles here. We're going to make our 3rd and 4th rectangle now. So click Geometry, right-click on here, click Rectangle again. The width of this rectangle. Now we're doing the rectangle on the left here. So the width of this rectangle is going to be 1, and the height is going to be 10 microns. And the position of this rectangle is going to be negative 7 and negative 5. So we build this object. Okay. So this rectangle shows up here, and we're going to put one more rectangle on here. Right-click to create the rectangle. This is also going to have a width of 1 micron and a height of 10. And the location of this one is going to be let's see, we would want to put this at 7 microns. And the Y would be negative 5 microns. All right, oops, looks like we put that too far. I think it should be 1 in here. There we go. All right. So we've placed all these electrodes. There is about a 12 micron gap here, 12 micron gap here. This is a 1 micron spacing here, you can see from the grid. And each of these electrons are 10 microns long by 1 microns wide. We need to add one more geometry element, and that's going to be a square. And the square is just going to fill this interior region. And the square is going to be centered at the origin, so it's going to fill this here in the middle. And since it's centered at the origin, we're going to choose that the position 0, 0 is going to be the center of the square. So the center of the square is at 0, x, and 0, y. If we build all the objects here, we'll get a square in there. Right? So these four rectangles represent the electrodes, as I mentioned, and the middle section here represents air. So there's going to be air separating those electrodes, and we would like to measure the electric fields, or simulate the electric fields within the air region. So at this point, you know how to build a simple two-dimensional geometry. If you click on here, you can see that there's actually like much more complex things you can do. You can actually create circles, ellipses, random polygons, parametric curves, points and polygons. You can also you can copy and paste objects. You can find the union and intersection and difference about the objects. You can do Boolean operations there. You could take an object and array it, so have multiple copies of it. You can mirror it, rotate it. There's a lot of operations you can do on each one of these objects that you've created. But you can see here that we created four rectangles, we created a square, and this last step here says form union. COMSOL will automatically form a union of all the shapes that you've drawn so that it has one unit object that it can use for the rest of the simulation. Okay, the second part here is we're going to choose materials. So why do we need to choose materials? Well, Gauss's law, the one we're solving in this, requires a permittivity. It requires that we know the epsilon for all the materials that we are going to be simulating. So one of the nice things that COMSOL has, it has a material database. If we right-click on materials and click Add Material, we can select some of these materials that are built into the software. So if we click on built-in materials here, we want this interior region to be air, so let's first select that. So we're going to double-click on this, and you'll see air show up here. So if you look through here, you'll notice that air has many properties. Click here, we can get a quick look at it. So air has a permittivity, a permeability, viscosity, electric conductivity, ratio specific heat, density, thermal conductivity, and so on. As I mentioned, COMSOL is a multi-physics solver, so it actually it can do simulations in all of these different domains: thermal, sound, acoustic, electrical, and so on. It turns out that in this simulation, the only property that we need is relative permittivity. That's why it has this check mark next to it. Okay. Again, Gauss's law just requires permittivity. So all of these other constants and variables are not going to be used in our simulation. So you notice that the relative permittivity of air, epsilon r, is equal to 1. All right, we're going to add another material here, just so you can see how this works. We can select this from this category, and we can select copper. Let's say we make our electrodes out of copper. Double click on here, and now we've created copper in our database. Now notice that copper has some different properties. It also has these properties defined, but the values of conductivity obviously are going to be quite different in copper versus air. You can see the conductivity difference is quite large. This is 0 for air, and copper has a high conductivity. But one of the things you notice, and I don't know, we haven't discussed this in detail in class, but the relative permittivity for copper and air is actually the same. Epsilon r for copper is 1. The epsilon r for air is also 1. All right. So now that we've defined these materials, we have to indicate which regions are which material. So if we click air here, we can select the first material. This is going to be this material is going to be air, and we have to go to the second material now, and we want to select these 4 electrodes as being copper. So let's click each one of those 4 here. All right, so now you notice what happens is that a shape 1, 3, 4, and 5, these 4 around the edges, are selected, and they're being assigned to being copper material. The air, the first one that we entered, that number 2 is selected as air, and you notice it says 1, 3, 4, 5 are overridden. So COMSOL has this mechanism is that when you enter your first material, all of the shapes are assigned to that material. So by default, once we created the air material, all the shapes were assigned to being air. And when we created this copper material and made some assignments there, these 4 electrodes were assigned to being copper. And you can see that those are being overridden. When we select the air, we can see that shape number 2 is air, but 1, 3, 4, 5 have been overridden by the assignment that we made subsequently. Okay, so we've assigned our materials now. Done with the geometry, done with the materials. Let's close this. And the next step is to define boundary conditions. So we're at this step here, adding the boundary conditions. Now, if you recall from your differential equations class, to solve a PDE, you must have boundary conditions. Just like to solve ordinary differential equations, you need to have an initial condition. To solve a partial differential equation, you must have a boundary condition. So what is a boundary condition? I'll show you. There's many different boundary conditions that we can indicate. In this particular simulation, our boundary condition is just a potential. We are going to say that this electrode and this electrode is at 10 volts, and this electrode and this electrode is at 0 volts. So this is what allows our solver to solve for the potential and electric field at every point in the middle here. Without those boundary conditions, the solver will not be able to solve anything. So let's look at the electrostatics interface here. So we said we wanted to do an electrostatic simulation, so that's why this interface shows up here. So if you click on here, it says the electrostatics is being solved in all of the domains, meaning like all the shapes that we just drew. That's fine. What is the equation being solved? COMSOL actually tells you exactly what equation it's solving. So we chose a stationary solver. So it tells us that we're doing del dot D is equal to rho V, and you should recognize that as Gauss's law. E is equal to negative del V. This is just a relationship between E and V. The definition of electric field is the gradient of the scalar potential. All right, so shows that. The thickness. So when we do two-dimensional simulations, COMSOL has this factor called the out-of-plane thickness, and it can actually account for very thick or very thin materials. If you set it equal to 1, essentially this ignores any out-of-plane type effects. So we're going to keep things simple here and not mess with that. The terminal sweep, I'm not quite sure what that is all about. Physics-controlled mesh, we can enable or disable that. In some types of physics, like fluids, COMSOL will automatically adapt the mesh. COMSOL will automatically adapt the mesh, refine the mesh near the boundaries where there are very sharp field gradients. All right, so we're not going to mess with this here. We're just doing a basic simulation. The dependent variables tell you that the thing that's being solved for is electric potential. All right, so this is telling us what we're solving. Now we have to put in some of the boundary conditions. If you right-click on electrostatics, you'll see all the possible boundary conditions that you can put in there. These are all essentially the constraints in the problem. So some of these boundary conditions show up by default here. Okay, so you see charge conservation, zero charge, and initial values. Let's see what that's all about. So charge conservation means that charge cannot be created nor destroyed. So the wherever it solves for charge conservation, it means that the charges no charges will be created or destroyed in that region. If we click specifically on the equation, you can see this first equation shows E is equal to negative del V, and this second equation here, del dot epsilon 0 epsilon r E is equal to V. This is called the just another form of Gauss's law. Okay. Charge conservation goes in by default because you have to have a default boundary condition for every single part of the domain that you're simulating. Okay, is there anything else we want to know there? Nope. The next boundary condition. So the charge conservation boundary condition goes on all of the shapes by default, in all of the in the interior regions. Notice the zero charge, by default, it's placed on all of the outer boundaries. Okay, you can see that where's the zero charge being enforced? All of these outside regions, the outer edge of the simulation. And the initial values here are being enforced on the interior regions here. And we're saying that these the initial values says that when COMSOL solves something, it comes up with an initial guess, and then it figures out the error, and it keeps on iterating until it gets to the correct solution. If you want to tell COMSOL where to begin, you can give it an initial value. So the first, by putting a 0 here, this is going to tell us that COMSOL is going to first, every single point on here is going to be assigned to 0 potential at the beginning, and then as COMSOL solves it, it will refine the answer and figure out what the actual potentials are at all those points. The zero charge, I don't know if I mentioned, it just means that there's zero charge everywhere on the outer boundary. So these are the default boundary conditions, but we actually want to put in the condition that we're trying to simulate. So we want to put in an electrostatic potential here, 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 and here. All right, so how we do that is we right-click on Electrostatics, and we say we're going to set an electric potential. Right-click here. These boundary conditions apply to the interior, and then these boundary conditions, which are called line or surface boundary conditions, these would apply to the edges. Now, anywhere where you see a line in the simulation model. So let us click electric potential, and we're going to set an electric potential on, let's do the positive electrodes first. So 1, 2, 3, 4. All 4 edges of this electrode are going to be set to 10 volts. So we selected the 4 of those. Notice that those 4 lines, the line numbers showed up here. Right? If I click on it again, I can deselect it. I can click something here, so on, and I can deselect it. So what I would like to do is I would like to set the top electrode and the bottom electrode to 10 volts. So I'm going to click all the boundaries here, 1, 2, 3, 4, and then 5, 6, 7, 8. Top and bottom electrodes will set to 10 volts. I can put 10 here. And that's done. Now we're going to right-click on this again, and we're going to do another boundary condition. We will set these electrodes, the left and right electrodes, to ground. So ground just means 0 potential. We could have also used the same type of boundary condition. We could have used electric potential again and just set the value equal to 0, or we can just use the ground, which is set to 0 automatically. So we're going to select the left and right electrodes, and we're going to set all that equal to ground. Okay, so at this point we've set a scalar potential everywhere. We have these 3 default boundary conditions. So at this point we can now mesh the model. So if I go to mesh and I click build mesh, you'll see that it breaks up this model into smaller elements. Okay, why does COMSOL do this? Is that it's a way to numerically solve for the electric field without having an analytical solution. So there is actually an entire class on the topic of finite element modeling that, if you're interested, it's offered in our ME department. But there's a lot of theory behind it. We're not going to go over the details of it. I just want to mention a couple things. The partial differential equations have to be solved numerically. And the way that COMSOL does this is actually an excerpt on one of the COMSOL's help files, is that you can approximate any function as a combination of piecewise linear sections. So you can see this random line here, the blue line here, can be approximated as a series of linear segments drawn in the purple dashed line here. And the more elements you have, the more effective that approximation is going to be, or the more accurate that approximation is going to be to that line. So the way that COMSOL describes is that this solution can be expressed as a linear combination of basis functions, multiple basis functions, one for each element that you've drawn. So you can see here that we've broken up the segment into 7 elements. And the solution at any one of these points is a linear combination of the basis functions, which have a value of 1 at the respective nodes and 0 everywhere else. So we're not going to go into the details of the mathematics of that. What the main points I want you to get out of here is that this line can be approximated by a series of piecewise linear segments. And the more segments we have, the more accurate that those segments can model that line. So in the case of the simulation, the line is the actual scalar potential that we want to figure out at each point in space. So what we're trying to do is we're trying to find the scalar potential everywhere in this xy plane here. All right, so we're going to break up this region into a bunch of small elements. Now, this idea of discretization was showing you in 1 dimensions, but the actual simulation that we're doing here is 2D. All right. The main point, takeaway point I want you to come away with here is that the more elements you have, the more accurate your finite element approximation is going to be. So by default, COMSOL has created a bunch of elements here. It creates a complete mesh consists of, let's go up there. Complete mesh consists of 626 domain elements, 104 boundary elements. Now we can refine this mesh if we'd like. We don't have to, but we can. If we want to make this a little bit more fine, we can select let's say finer, and we can remesh, and you can see the elements became smaller. Now, do you have to do that? Not necessarily. Usually, there's a trade-off between computation time and the mesh refinement. So the more you refine the mesh, the more accurate the results are going to be. But of course, you're going to have more elements, so it's going to take more memory, more time to solve. For a simple simulation like this, you won't notice a time difference, but for large 3D simulations, you definitely will. All right, so we've created the mesh here. Now the next step is to actually do a solution. So by default, the stationary study has already been created for us. So we can click on this and find out some more details. This will actually, if we want to click here, it'll plot the results while solving. That's not really that important for a fast simulation like this. But it tells you what we're simulating here. We are solving the electrostatics, the physics interface here. That's why there's a check mark here. We are solving for dependent variables which are described in the physics. So if we go to electrostatics and we go down to dependent variables, we can see that what we're solving for is V. It'll also solve for E. And mesh selection, we selected mesh 1, which is up here. And the study extensions, Not quite sure what that is about, so let's leave that alone. All right, so we've defined the study. Actually, COMSOL has defined the study by default. So now we can click Compute to compute the study. So the way you can do that is to right-click on the study and click Compute. The second way to do it is just to click F8. And the third way to do it is to actually just go up here in the toolbar and click Compute. All right, so this is a relatively simple simulation, so COMSOL is able to find the electric fields quite rapidly. And it's showing you a default plot. So let's go to the results tree now. Notice before the results tree was completely empty, and now it's and now there's some data here. So if we right-click on the results tree, we can create various types of plots. We'll get to that in a second. So if you click on here under data sets, you'll see that this is your study 1 solution. This tells you that COMSOL has calculated a solution here. At this point, it's always good to save the file. Okay, because if a simulation takes a very long time to generate the results, you want to make sure those results are saved in case something crashes. All right, this just tells you that the data is in here. The derived values and tables we're not going to be dealing with too much here. I might show you that in some future simulations. Right now, I just want to show you some of the plots that you can generate. All right, so let's click here. And this is one of the plot groups that was made. By the way, if you ever want to disable a plot group, right-click on this, and you can go to Disable, and that plot will no longer show. You can define multiple plot groups. So by going to Results, you can create a 3D plot group, which is a 3-dimensional plot, a 2-dimensional plot, or a 1-dimensional plot. And these also Polar and Smith plots are for doing transmission line type analysis. So let's enable this. This was a 2-dimensional plot, by the way. So let's enable this again so it shows. Notice that this says 2D plot group. If you ever want to replot a group, you just click Plot. Okay. Now what does this group contain? We click on this. We can see that there's just one plot under here. The reason why a plot group is set up like this is that you could actually include multiple plots in the same group, and those plots will actually overlay each other. Okay, so electric potential. Let's see how much battery left. Okay, good. If we right-click on a plot group, it will bring up all different types of options, the different types of plots that we can make. Now the ones that we're going to work with today is the surface plot, and then the arrow plot, and then also the contour plot. So let's draw the let's add an arrow surface plot. Since we already have a surface one here, notice that this is a surface plot, and that shows this color graph of the scalar potential, and we'll soon create an arrow plot after this. Before we do that, let's first look at this contour plot here. All right, so you have this, a surface plot is a 2-dimensional plot, and you can see here that there's a label here. You can select what expression you want to plot. All right, so we want to plot the scalar potential, so we put V here. But you have other options of things that you'd like to be able to plot as well. If you click under Electrostatics, these are all the options that you have. There's many things that you can plot. You can plot the current densities. You can plot the charge densities. You can plot the displacement field, the electric field, the polarization, different material properties. You can even plot things related to the geometry. All right, so but we're most interested in the scalar potential, so we'll click on this, and that brings up V. All right, so we want to plot the scalar potential, and the units is going to be in volts. All right, you have other options here if you'd like to do gigavolts or kilovolts or whatnot. Let's keep this volts here. All right, and if you click this, you can change the default description. That's what appears up here, electric potential. We don't need to really change that, so that's fine. The title type is automatic. You could also change this to manual if you'd like. All right, now what you notice here is this is a colored plot, and the colored plot has a color legend on the right hand side. So what this is showing us is that the places that are red in color or brown in color is around 10 volts. The region that is blue, completely dark blue here, is 0 volts, and you can see the color scale going from 0 to 10 volts. Remember, we put 10 volts on the top and bottom electrodes, so this makes sense. Top and bottom electrodes are at 10 volts. The left two electrodes, the left and right electrodes are at 0 volts, and you get this interesting pattern in the middle. All right, so this this green area here, so this shows that this whole center region is at about 5 volts. And you can see by the color here how that scalar potential is changing as you go from one point in space to the next. High potential, low potential. If you click on the range here, this color range is determined by default, and I recommend you stick with that. If you want to change the manual data ranges, you can do that. These are more or less more advanced settings that you want to deal with if you know that there's a specific range that you want to plot, and perhaps ignore the rest. Let's take this off here. All right, so let's just have the auto scaling on. You can choose a color table that's rainbow, thermal. These are different color mappings. The rainbow one is fine. This is to include a color legend. You can include a wireframe if you like, but I recommend just sticking with the defaults. There's not much we need to change here in terms of the quality and inherit style. So this is just a plot of the scalar potential. At every point in space, the color is indicative of what the scalar potential is in that region. So it's a really nice visual tool to be able to visualize the electric field. Now if I want to save a plot, I can click on this snapshot here, image snapshot, and then I can output it to a file, and I can select what I can include all of these things, or I can include none of them if I want. So this time I can save this to a PNG file, scalar potential. So let's save this to my scalar potential. All right, and I'll save it in PNG format. So I can just save that image there, and then I should be able to see that in my directory here. And that's how you would save your graphs for a report. So I would like for all of you to actually save the images that you work on, just to show me that you've completed this study. All right, now that I've shown you what the simple surface plot is, I'm going to add to this. So by right-clicking here, I'm going to add a surface plot, an arrow plot. So as you know, we've been working with vector fields, right? Electric fields are vectors, not scalars. So in order to represent that, we have to have an arrow at every single point in space. So that's what this arrow surface is. It's a way to plot vector fields. Excuse me. All right, so again, you can call this whatever you would like. You can select what you want to plot. So the x component of the arrow is going to be es.ex. That means it's the x component of the electric field. EY is going to be the y component of the electric field. As I mentioned before, you can select other options here as well. The displacement field, the polarization field, and so on. Obviously, at this point, we're interested in just the electric field. Okay, now I click plot, and I should see some faint arrows here. Now, if we zoom in here, we can actually see them a little bit better. All right, now COMSOL generally makes the arrows a little bit small. I like to make them a little bit larger. The way you can do that is by going down here and click on the coloring and style region, and you can click the scale factor, and you can make the scale factor a little bit larger so you can visualize those arrows a little bit better. Alright, it's nice to be able to see the arrows because it shows you the magnitude and direction of the electric field at every single point in space. So if we zoom in just on this region here, you can see that the electric field goes from high potential to low potential, which is what we'd expect. All right. Now, if we want to include more arrows so that you can see the field in finer detail, you can increase this number here. So let's say we increase this to 25, and we increase that on the Y side as well. Let's just first do the X. You can see it creates more arrows here. By increasing this number here, it'll also create more in the Y area. So this will then basically draw more arrows for you. Alright, so something interesting that you notice about the quadrupole here is that you get very strong field gradients at the edges, but in the middle, the field gradients, you can see that there's almost no electric field. So if you were to put a charge in the middle here, there would actually be very little low electric field acting on that charge. As a result, that charge could actually be trapped in the middle. That's what these quadrupoles are sometimes used for trapping charges. So this is an arrow plot. So I'm going to go back to 20 here, replot this, and I can change the scale a little bit here. Actually, I liked it better with 25. Let's keep it there like that. Increase the scale again a little bit, and I'm going to save this file. We can call this scalar potential and E field. So we'll save that there. Now I'd like to add another type of plot to here. I don't want it to overlap with this, so I'm going to create a new two-dimensional plot group here. Right-click on results and click another two-dimensional plot group here. Notice that it starts off with just the geometry. It's fairly empty. And within this, I'm going to create something called a contour plot. So I go up here and click contour. Right? And we're going to create contours of the scalar potential. I click this here. All right, now what you can see here, what has been done here is that this is a contour map. I don't know if any of you have seen a topographical map. If you go hiking, the topographical map draws lines at equal elevation. So at a particular elevation, it'll draw a line showing all the points on the mountain that are at that elevation. The contour map here does something quite similar. Each one of these lines represents one potential. So you can see that near the electrodes, this line here represents 10 volts. The next line, next line is a little bit more red, 9.25. So every point along this line is 9.25 volts. If you go down here, every cyan colored line is 3.25 volts. All right, so every point along these lines is at the same potential. It's another way to visualize the electric field. So I'm going to right-click on this and also add the arrow plot. No, we can add that. I'm going to increase the number of points again to 25 and increase the scaling factor. All right, and you can see the difference between this plot is essentially showing the same thing, except the color is filled in everywhere. In the contour plot, instead of drawing shaded colors, you basically just get these contours of equal scalar potential. It's another way of visualizing the same field. So let's save this one too. So we'll call this contour plot of scalar potential. So you're free to call the files whatever you'd like. And let's see if that showed up. Yep, here we go. All right, and this file is saved here. All right. The one other thing that I would like to show you is how to create a one-dimensional plot. So if we right-click on this and click 1D plot group. Now, what I want to do here is I would like to create a plot of the scalar potential along this line. So going from where my mouse is right now, going across here horizontally like this, and then ending here. So if we were to draw a line from here to here, I would like to plot the actual voltage values at every single point in space along that line. So what I can do is go to this one-dimensional plot group, and within here we're going to create a line graph, and we can plot along any one of these lines. Now, oh, this is a bit of a problem because I didn't define a line going from here to here. All right, so let me see if there's a way around that. Ah, we can define a cut line, I think. Yes, we can define a cut line here. Let's see if we can figure out how to do that. Dataset cut line 2D. Ah, when you click cut line here, if you click define cut line, it automatically creates something called a cut line down here. And now I remember how to do this. So if we want to do, if we want to create something like a line across here to use for data plotting, so we can define this cut line the way I just did. You go to the line graph, and then you click on this, define a cut line, and then you'll see something show up here. Now, here what we can do is we can define 2 points in space. So if we look at our geometry here, we would like to go from the point 0 to x equals -6 microns and y equals 0 to x equals 6 microns, y equals 0. So let's go from x equals -6 microns and y is equal to 0. That's the first point, and then the second point is going to be 6 microns. The y is still going to be equal to 0. All right, so that will define this cut line here. And when we go to the line graph, we would like to, the data set that we'd like to plot is along this cut line. So if we click none, we won't have any data here. All right, so we have to identify that cut line that we created as the source of the data. The thing that we want to plot is the scalar potential, V, and we can select expression here. So this is what goes on the x-axis, and the expression, this is going to be the x location, and the units is going to be, we can say microns. Select microns as the unit. Plot this. All right, and you can notice that the x-coordinate is showing up on the x-axis, and the y-axis is showing electric field. Again, this is the expression for the x-coordinate. This is the expression for the scalar potential. Notice that the electric potential is 0 at the left and right side. So it's basically communicating the same information that this plot showed. So it's 0 volts here, it's 0 volts here, but in the middle it increases to 5 volts. All right, but the nice thing about a one-dimensional plot is that you can easily, it just gives you more quantitative information. You can change the x-axis to a log scale if you want for some of these types of plots. We don't need to do that here. You can show a legend if you'd like. Again, we don't need to do that here. Let's just save this plot. So we'll call this scalar potential 1D. And that data will be saved. Now another thing you can do here is you should be able to export this data. So if you right click on here and we click add image, no, not quite. Let's see, export a 1D image. I think that's it. Oh, export data, let's try that. No, not quite. Let's try this one. Add plot data to export. So we created this plot, and if we click on here, notice that this plot 1 showed up. So I didn't do that correctly the first time. Let me just show you again from the beginning. I delete this. So we made this line graph here, and now we want to export it. So right click on this, add plot data to export. And then under export, this thing shows up. So this has data for every single point in space going from left to right. So you could save this data to a spreadsheet. So we can call this 1D plot. And it'll save it as a text file. Let's say 1D plot, 1D scalar potential. You can save it as a text file or as a CSV file. CSVs will open easily in Excel, so let's save it as that. And click export, and the file will be exported. Now if we go here, we can, let's see if we can find that file. "1D scalar potential plot." See, it's even showing up as an Excel file. So I can click on this, and you can see all the values. This is the X value, so -6. This is the X value in microns, and then the height, the second column here, is the scalar potential. You can see that it goes up to 5, and then it goes back down to 0. So this is a way of exporting numerical data outside. All right, so I initially planned on 30 minutes, but it looks like it took longer than that. But the main points of the simulation, going back to here, so what did we do? We created a geometry, and then we added the boundary conditions, we meshed, we computed the solutions, and then we plotted and analyzed the results. And as I mentioned, the reason we do simulations is because you'll have a geometry that might be too complicated to solve by hand, and hence you can put any arbitrary geometry into COMSOL. If you put in the appropriate boundary conditions, COMSOL should be able to solve it. Okay, so what I would like you to do for your assignment is I would like for you to simulate this just like we've done here. And I would like you to bring printouts of the different printouts that I did, and also the Excel file showing the numerical data. And I would like for you to bring that to the next class period. If you have any questions, please email me. I hope this was an interesting class for you. And as I mentioned before, I do expect us to do 1 or 2 more simulation exercises like this, where we'll be doing not just electrostatic potentials, but also things like the current densities and so on. So it's a good tool for you to know, not just for electrostatics, but if you become familiar with COMSOL, it'll be useful for you for doing stress and strain, other types of electromagnetics, thermal simulations, many different things. Okay, so I will sign off here for today, and I hope you have a good rest of the week, and we will see you in class next time.